Hello everyone, I have been very busy lately and not posting anything. Sorry about that, but I have had a very busy semester. I have two teachings, one of them meeting every single day. Then I had two talks to give in October. I went to Bowling Green State University for a colloquium talk, and then I was in Eastern sectional meeting of AMS, and there I also gave a talk. And generally life has been very busy with job applications and stuff. The AMS sectional meetings, if you're not aware of them, these are parts of AMS's programs. They happen multiple times during the year and in different corners of the United States of America. And I attended this particular one. They have a quite high registration fee that fortunately my department agreed to cover for me along with travel expenses and stuff. So I have some piece of math to share with you today, and that regards this example of a one-dimensional space that has infinite H1 measure under all homeomorphisms. Previously I had a very convoluted example using some non-trivial facts about the topology of continua, but talking to Piotr Hajlasz, he came up with an amazing, simpler example, which is also stronger because it's a compact one. So you have this two fixed points, say 0 and 1 in the plane, and you have a infinite collection of short path connecting them, disjoint. We claim that if f is any homeomorphism from this x equipped with the Euclidean distance to another metric space, if this is a homeomorphism, then H1 computed inside Y, that is Hausdorff one measure with respect to d distance of image of X, will have infinite measure. That means you cannot make this a finite H1 measure space under homeomorphisms. This fact is not true for Hausdorff measure 2 and 3 and more. The reasoning here is much simpler than the reasoning in the original example I had given, and that is, we know that f of 0 is not equal to f of 1 in the target space. They map to different points. They may be very close, but they are not the same points. Now, if you take one of these paths, one of these segments, say EJ, then, so here's a proof. F of EJ is a compact connected set because it's image of a compact connected set. Connected set joining f of 0 and f of 1. And here comes the key fact about Hausdorff one measure. H1 measure of such a compact connected set is never less than the diameter of the set, which will be more than the distance of these f0 and f1. And let's call this non-zero number delta. Okay, but then you have many of these EJs, so, and because f is homeomorphism, these do not intersect basically. So their intersection is just the 2 points f0 and f of 1 for every j and every j prime other than j. So that means they are pairwise disjoint in the image, and each one of them has length at least delta, Therefore, H1 of the image of E, and not E, of my set is greater than or equal to k many of these deltas, but for every k in natural numbers. So H1 of f of E is infinity. That's the end of the proof, using really no sophisticated topology, and the only metric fact we used was this fact between diameter and H1 about Hausdorff measure. So let me just convince you why for Hausdorff 2 measure this doesn't have to be the case. So you can have these two really far away, and then you can have them connected with a two-dimensional surface that runs like really narrow. I'm trying to make it actually two-dimensional. Otherwise, I could also just connect with one line. Technically, it's a compact connected set. But even then, even if you insist on locally being homeomorphic to R2, you don't have any guarantee, any lower bound in terms of just diameter for H2. But for H1, you do. Okay, so that just makes the counterexample more compelling. Here are like the f of E j's for different j's. Okay, hopefully you liked it. I may have forgotten it. This was given to me, this counterexample, by Piotr Hajlasz. So I will have more content as often as I can, but again, I can't promise much. Hopefully next semester will be a bit better. Thank you so much, and have a nice day.